is being publicly streamed.
All right. So now I hope we can start now. Um, okay. So last time uh, we see last time we saw about orthogonal. What do we mean by orthogonal vectors? And we also saw set of orthogonal vectors. Okay. So sorry, we didn't see that. Yeah. Last time we saw inner product spaces. Okay, to be correct. So last time we saw what is an inner product, what is the norm on a vector space, uh, and we also saw that inner product is an abstract version of dot product, which is available on R2 and R. Okay, orange and Rn. Right. So today's aim is to discuss orthogonality, orthogonal basis, and projections using the inner products. Okay. So I will talk about each of the topic uh, in today's discussion. Uh, and if you have any doubt at any point, you are not able to understand anything which I say, you may ask questions. Before I start, let me announce about Quiz 2. Quiz 2 is on 3rd of August 2025, and the syllabus of the quiz is week 5 to week 8. Okay. Uh, so there were a lot of queries about the syllabus of quiz 2. So this is the syllabus for quiz 2, week 5 to week 8. All right.
So I
Now
have
let
a
me,
doubt.
yeah,
The we're starting week 8 today, right?
yes.
Okay, and what about orthogonality? It was last week, is it?
So orthogonality, today we will discuss orthogonality.
Okay, okay. Thank you.
Right. Uh, okay. So let me start with comparison that we saw in the last session between dot product and inner product. Okay. So I hope all of you are comfortable with dot product, right? Is there anyone who is not comfortable with dot product of vectors in R2 or vectors in R space? All right, good. Right. So let's say in R2, whenever you have two vectors, um, let's say this is my 1 cross 3, 1 comma 3, and there is another vector, let's say minus 1 comma 2. All right. So you can think of that they are vector lying in an R2 plane where the axis, which is running from left to right, is the x-axis, and the axis that is going from bottom to top is the y-axis. I hope all of you are familiar with these notations. And the point in the middle where these axes intersect is called the origin, and it is has the Cartesian coordinate to be 0, comma 0. All right. And you have two vectors v and w. Right. Now, uh, can anyone recall what is the dot product of vector v with w?
So it would be 5 here. So x1, x2 plus y1,
Yes.
y2.
Yes. So it is 1 times minus 1 plus 2 times 3. Uh, right. So it is going to be minus 1 plus 6, which is going to be 5. Right. So this is what dot product is. Or in generality, if I want to write, let's say if there are two vectors, x1, x1, y1, dot product with x2, y2, then it is defined to be x1, x2 plus y1, y2 as you mentioned, right? And this type of dot product can be generalized to Rn, where you have, so this has generalization to Rn. So in particular, if we have two vectors, let's say x1, x2 up to xn, yeah, x1 up to xn, and y1 up to yn, then the dot product is defined to be the the sum of the coordinate wise multiplication. All right. So this is the inner product. This is the dot product that we define in higher dimension of Rn. Obviously, this is for n greater than equal to 3. Sorry, for n greater than 3, it is hard to visualize. What do we mean by this dot product? But this still makes sense, right? So similarly, because we have seen that vector space has structures like we observed in the Euclidean space or Euclidean plane, that is addition of two vectors reduces another vector, or a scalar multiplication of a vector is another vector, and then other properties. So we capture these ideas in an abstract space, which we call to be the vector space, right? Uh, so plus is the addition of two vectors, dot is the scalar multiplication, and our field is R. So the scalars are coming from real line, right? So we have seen, we have generalized, we have abstractified the Euclidean planes or Euclidean spaces to a vector space over R. Similarly, this dot product abstraction, if I abstract this dot product, so it gives me inner product space. Okay, so this gives me something which is called inner product. So dot product here is inner product in the vector space, right? And inner product, as you notice in the case of dot product as well, dot product is a function from v cross v, okay, to a real number r. It produces a real number, right? So dot product was a map from v cross v to r. Similarly, inner product is also a map from v cross v to r. Sorry, in this case, it was r2 cross r2 to r, or in general, Rn cross Rn to r. Here it is a product, it is a space, it is a function from v cross v to r. All right. And this product satisfied these following properties, this function. So first property is that the inner product of the vector with itself has to be positive or zero. And if it is zero, with equality holding only at v is equal to 0. The second property was it is linear in the first coordinate. All right. So this is a quick revision to what you saw last week. Third property was it is by linearity. You also need to verify this a scalar product as well. So it is also you can take the scalar out. So C v comma v2, and the fourth property was that it is symmetric. It doesn't matter what order you write your vectors in. All right. So right. So this is what we saw that a dot product, abstract version of dot product is inner product on a vector space. So now the very first example of inner product uh, on uh, on Euclidean space is the dot product itself. All right, it makes sense to all of you. Right. Now in R2 or in Rn, we have length as well. We have a concept of length. Right? Length of a vector. So now what is the length? Length is basically the distance between uh, origin and the point 1 comma 3. For that is also known as the length of the vector v. All right. So how do we define the length of a vector? So length of a vector v or x comma y in R2 is, what is this? It is
Put x square plus y square.
square root of that, right? So this is the length of the vector. Similarly, in the case of inner product spaces, we have something which is called norm of a vector. Okay. So which is defined to be uh, norm of V is square root of the inner product of vector V with itself. All right. So they have the similar kind of uh, you can see that how similar they are in nature.
So the norm
Right?
of the vector is also equal to the length of the vector, right?
So norm is the it's not the it's the length of the vector if you're taking your vector in R2 with the standard dot product. Okay. So
Okay.
this norm is a general term. It is defined for any vector space, but length is a specific term which is defined in Euclidean spaces or Rn. Okay, so there is a clear distinction. So here my V, this vector space V, this could be any general space. It could be M to R, right? It could be set of matrices. It could be set of polynomials of degree smaller than equal to n. It could be a set of all symmetric matrices. Okay, it could be any space. It could be vector space. It could be a hyperplane. It could be a hyperplane passing through origin in some Rn dimension. But here the space is fixed. It is R2. So that's the difference. So if it's in R2 or in Rn, then it is length. Otherwise, in general terms, it is called the norm. But yes, norm is a generalization of a length. That is true. All right. So this is what we learned last time. We
S-
also see
so then, in order to define a norm, do we always need to define the inner product? Is it mandatory?
no. Good question. If you are defining a norm on a in a vector space, then we define it using this. But there could be one can define norm independent of vector space, independent of the inner product space.
Okay.
So in this case, the norm is defined in terms of inner product that you can clearly see, but it is not. It need not to be true always. Yeah,
Okay.
you can define norm independent as long as it satisfies the conditions of norm. Now, can anyone recall what are the condition of being norm? So norm is again a function from V to R, R positive or equal to 0, right? So now what are the properties that this function is to satisfy in order
Uh,
to call itself a norm?
I remember
Yeah.
first one was triangular inequality. So,
Good. First one is triangle inequality. That is true. So the norm of V plus W should be smaller than or equal to norm of V plus norm of W. Now, the second one is that if you take the scale, if you scale your vector by C and you take the norm of that, this is equal to multiplying the mod C with the norm of V. Okay. And the third property is that the norm is always positive or zero. It is zero, norm is zero, if and only if the vector itself is zero. Okay. So this is the space of so any function on vector space V satisfying these three property defines a norm. But if we are working with the inner product space, that means I have a vector space with the inner product on it. This is what this is how I define my norm to be. Okay. All right. Yeah. We also know angle. We can also capture angle in Euclidean spaces. So in particular, for example, in this case of V and W, there is an angle between V and W. Okay, that is called theta. Now I can find out this angle in terms of the dot product and the length of the vectors. All right, and the formula goes like this: that cos theta is equal to the dot product of V and W, dot product of V and W divided by norm of V and norm of W. All right. So this is how we define our. This is how we find out the angle between the vectors. All right. In the setup of dot product. Okay. So now let me talk about an example of an product just to complete the recap. Okay. You take your vector space to be R3. All right. And you take your norm to be you take your inner product to be the dot product. All right. And let's say your V1 is 1, 0, 0, and your V2 is 1, 1, 1. So now what is this value? V1 dot V1. What is the inner product of between V1 and V2?
1.
1.
Right. Correct. Now let me change the norm. The inner product. So instead of taking the dot product, usual dot product, let's take 3 times x1 . All right. So this is what I have taken.
3.
Plus 3 times x2 y2 plus 3 times x3 y3. All right. Now what will be my dot product of v1 v2? It is
3.
direct. Yeah, correct. It is going to be 3 because I just multiplied 3 with this. Okay. So now let me ask you this then. If I define my inner product of if I define my inner product to be, yeah. So let me just copy this one. If I define my inner product to be just this 3x1 y1, so is it an inner product?
No.
Which property it does not mention?
Inner product is equal to 0 if and only if it is zeros or multiple.
Right. So it is not correct.
So I
So
could not understand why it is not.
so did you check all the properties? So
Which
you
property?
check one by one property. So you check first property. What are the conditions that it needs to satisfy? First condition, does it satisfy the first condition?
T1 V
is equal to 0. No, it does not.
right? So is it inner product then?
No.
Right? So okay, good. Um, yeah. Okay, so I have another example before we move on to orthogonality, and this example is slightly, I don't know whether it's new or for you or not, but I'm taking a different vector space. So it is a vector space of polynomials. It is a vector space of polynomials of degree less than or equal to 2. Okay, and my inner product that I'm defining is basically, so if I take if I take two polynomials, that means a0 plus a1x plus a2x2 x squared, b0 plus b1x plus b2x square. It is defined to be ai bi from 0 to 2. All right. So now for v1 to be equal to x plus x square and v2 to be, okay, so now what is 1 plus 3x, inner product of 1 plus 3x and x plus x square?
It's 3, right?
Yeah, can you tell me how did you do that?
This 1 plus 3x plus 0x square, comma, 1
Yes,
plus x square. So
correct. So it is a0 is 1, b0 is 0, right? What is a1? A1 is 3. A2 is b2, b1 is 1.
1.
Similar, a3 is a2 is 0 and b2 is
1.
1. So it's a simple computation. It is 3, right? Uh, so let me give you another exercise. Check that check that whether this mm, so let uh, px to be this and qx to be this, let px to be this and qx to be this, x square, and define the inner product between px and qx to be the integration from 0 to 1. All right. So now check uh, that it is an inner product space. This defines an inner product on V. All right. So yeah, you know how to do that. You need to check each condition, and yeah, one by one you can check that. You just need to first multiply and then calculate the integration. You will find out the detail. It might look tricky, but it is not. It is just computation only. Okay. So now after
So
this,
this,
yeah.
so the first condition would anyway be true here, and second condition also follows from distributivity, and third condition is also checked because if you multiply C with with one of the vectors, the integration gets multiplied with the constant, just the constant. And with V1, V2, it's because the integration is symmetric, so PQ and QP is symmetric, so it's symmetric.
Right. So it is clear, right? Like, so good. But for others who are having difficulty trying to understand at the very first class, they can try it out, and then it's a good exercise for you to check whether it's in a product or not. Okay, good. Now let's move on to discuss orthogonality. Okay, so again, I will use the comparison from R2. So in R2, we know that two vectors V and W that forms an angle of 90 degree. Then their dot product is what? The dot product is
0.
0, right? And how do we compute that? Because
Cos
V
90
dot
is 0.
W, yes, is this, and cos 90 is equal to 0. So multiplication with 0 gives 0. So this is the explanation. So uh, so then we say that V is perpendicular to W, and this is true in general Rn as well. Now this concept of perpendicularity uh, in abstract vector spaces translates to orthogonality, okay, or orthogon. So we say, so in general vector space with an inner product on it, okay, so we say vectors v1, v2 in V are orthogonal if their inner product is equal to 0, right? So for example, let's take the space of polynomial. Let me name something that space of polynomial. So let me name this space of polynomial because I will be using this again. Let's take P2x. Okay. So it's a polynomial of maximum degree 2 with determinant indeterminate x in terms of indeterminate x. Okay. So let's take this example of P2. So on P2x with inner product defined above, it is an inner product space. Now we check that P1 of x, P1 of x, which is given by x plus x square, and P2 of x, which is 4. Now what is P1 orthogonal to P2? So what is the inner product of P1, P2?
It's 0 because if you match the
It is
coefficients.
exactly. So 4 times 0 plus 0 times 1 plus 0 times 1. So it is 0. So this implies that P1 is orthogonal to P2. All right. Now let me, so if that is clear, let me take another example of P2x itself and P2s with the different inner product that I defined with the integration. So let me write it with I subscript. As one of you already pointed out, that is an inner product space. So let me just start working with it. Okay, so this P2x, this set of our polynomials of maximal degree 2 with the inner product given by the integration. So now let's check whether the above set of vectors P1 and P2, which was P1 was x plus x square and P2 was 4. So are these two vectors orthogonal to each other? So for that, we need to find out their inner product. So it is x plus x square times 4 dx. Okay. Now what is this? What is this integration? What is the value of this integration? Can anyone solve that?
So it's 4 into 1 by 2 plus 1 by 3. So it's 5 by
Okay.
6.
So it is not 0.
20
Right.
by 6.
It is not 0. That's not one. So it is not equal to 0. Right?
Yes.
So that means they are not orthogonal, which were orthogonal with respect to some other inner product, but they are not orthogonal with respect to some other inner product. So orthogonality depends completely on the choice of inner product that you have started with. Okay. Um, right. Now, clearly you can notice that uh, 0, 0 in V is orthogonal to itself as well as uh, to every other element in um, your vector space, your inner product space. Okay, you can take this as a fact, or in order to, if you want to prove this, so 0, comma 0, we already know that 0, inner product of 0 with itself is 0, right? By the inner product condition, right? So that is already known. Now to prove that 0, comma u is 0 for all u in V, we need to define a linear map uh, from V to R, okay, which is taking, so we call this linear map to be LU. So it takes V and it maps to V comma U. All right. Now any linear map. So this is a linear map. You can check it is a linear map because of the linearity at the first coordinate. This is a linear map. And now we know that any linear map takes uh, 0 to 0 to 0, right? So this implies that 0 comma u is equal to 0. Okay. And you can define this for any u, and this map, above map, can be defined uh, since choice of u is arbitrary in above definition. Um, so is 0 for all u in V. All right. Yeah. So you can either, if you understand this proof, it is completely okay with me. If you don't understand, that is also okay. You just need to understand. You just need to know this fact that 0 is orthogonal to itself as well as to every other element in the inner product space. Okay. Any question? All right. Okay. So now we know that when one vector can be orthogonal to another vector, now we can have a mutually orthogonal vectors. Okay, and we can form a subset, and there can be a subset of orthogonal vectors. Okay, so let me just uh, mention that orthogonal subset. So for example, you consider this set of vectors, which is 1 0 0, 0 1 0, and 1 1 1 0. 0 0 1. All right. So you consider this subset of vectors in R3 with dot product. All right. Now, what do we notice here? That each of the vector is orthogonal to itself. So clearly, let's call them E1, E2, E3. E1 dot E2 is 0. E2 dot E3 is 0. E3 dot E1 is 0. So each vector is orthogonal to other vector. In other words, they are mutually orthogonal to each other. So mutually orthogonal to each other. Such subsets of vector, okay, are called orthogonal subsets. In your inner product space. Right? Now let me give you one more example, and I will ask you guys to verify that. So consider these space 1 1 0 0 0 0 1 1. Alright. So now consider this subset of three elements in R4 with dot product. So is S consider case one. So check S. Okay. So is the first space first subset an orthogonal subset? Oh, am I audible?
Yes, sir.
Yeah. So my is my question clear to all of you? So I have written a set. I've written a subset of R4. Now question is that subset of R4 forms an orthogonal subset in the given inner product space? Okay.
So the first one does not.
That's one does not. Right. And can you give me why? Can you tell me
V2
why?
and let's take V2 and V3 so
Yeah.
it becomes
Yes.
3.
Yes.
Yeah, it becomes 3.
Right.
Yeah. Even if you
Right.
check V1 and V3, that also.
Exactly. So V3 is the problematic vector. If I remove that vector, then it is orthogonal subset, right? If I remove, let's say, this vector, so is it an orthogonal subset now?
Yes, sir, it is.
Correct? Right. Now, what about subset given in option 2? Is it an orthogonal subset?
Yes, sir, it is.
Correct. And if I remove any of the vector from this subset, is it remain orthogonal subset or not?
Yes, sir.
Yes, it still remains orthogonal.
Right. So any subset of orthogonal subset is again an orthogonal subset. All right. Uh, so let me write down this uh, point. So any subset of an orthogonal subset is again an orthogonal subset. Right. Now there is an important fact about these orthogonal set. So check for subset 2, subset given in option 2, whether they are linear independent or not. Okay. So since you are working in R3, how do we check that given a set of 3 vectors is linear independent or not? How do we check that?
Take the determinant. If it's not equal to 0, it's
Exactly.
linearly
Exactly.
independent.
Exactly. So is the determinant of subset given in option 2 non-zero?
Yes, sir.
Okay, good. So that means uh, the subset in option 2 is linear independent as well. So it is orthogonal and it is linear independent. So now let me write down this fact that set of orthogonal vectors are forms a linear dependent set. Okay, so that is always true. Orthogonal subsets are linearly independent also of inner product space. All right. So, in other words, in order to obtain the orthogonal basis, what do I need now? I already have the linear independence. What is the other requirement to form a basis? So I want to obtain an orthogonal basis. Okay. Now to obtain a basis of a vector space, there are two requirements, right? What are those two requirements? First is linear dependence. Second is, what is the second one?
Minimally spanning.
Minimal spanning, right? So if I have minimal spanning, if I have a minimal spanning orthogonal subset, then do I have a basis as well?
Yes, it's a
Right.
minimal spanning set. Yes.
Yeah. So any minimal spanning set, any minimal spanning orthogonal subset forms a basis of the inner product space. All right. In particular, they form a orthogonal basis of inner. Okay. So let me write that down as well. So because of our fact, we have that any minimal spanning set, any minimal spanning orthogonal subset of vectors in inner product space forms an orthogonal basis, right? All right. So forms and bases, and they are orthogonal as well. Now let me write down what do we mean by orthogonal basis. So we say a basis is orthogonal if we say basis, let me write E1 up to, or let's say B1 Bn of uh, B within a product this to be orthogonal if B1 to Bn is an orthogonal subset. All right. So this is your definition, and this is your another fact. Right. So is it clear now? So in our case of this option 2, so this option 2 is a minimal spanning set, right? Why it is minimal spanning?
Because in Rn, if
Because
we consider
yeah,
n vectors, then and they are linearly
Right.
dependent, then they are minimally spanning.
Yes. No, for spanning, they need not to be linear independent. Uh, they span if any vector can be written in terms of these three vectors, then they are spanning. But in our case, we have shown that it is linear independent because they are orthogonal sets, so they are linear dependent. And we have also, because they are in 3 number, and we are looking at R3. So R3 is the minimum number.
just it should be
Oh,
in R3. It should be a maximally linearly dependent set. So that's the
right.
in
That's, yes, exactly. Uh, so that's why they form an orthogonal basis. So option 2, subset in option 2 is the orthogonal basis. All right. All right. Now let me give another example of a different nature.
Still, can you
Let's say your
scroll up
vector.
a bit?
Yeah, sure. A bit more.
No, sir, it's fine. Thank you, sir.
Okay. Yeah. So for another example of vector space, let's say M2R. Okay. So it is set of all matrices of order 2 cross 2 with real entries. Okay. Now we define the inner product. Let's say I'm calling it to be inner product on matrices, similar to uh, yeah. I define the inner product on matrices similar to the standard inner product. Better to write other notation. A11, A12, A21, 22, B1, B2, B1. Define it to be A1, right? All right. So now, uh, clearly this is an inner product. You can check. This is an inner product space. Now, I have given the set of vector, which is 0, 3, 0, 0, 0, 0, 4, -2, 0, 0, 5 by 2, 5. All right. So the subset in M2R now is as an orthogonal subset. That is the first thing. And second thing is S forms a basis. Okay.
It is an orthogonal subset,
Okay.
but it
All right. Good.
does not form a basis
Why?
because it is not minimally spanning.
Correct. No, not a minimalist. Not a minimalist. Can you give me a Can you give me a matrix that is not in the span of these three vectors?
Any matrix with the first entry one, like A11 is 1, will not.
Right. Correct. Exactly correct. Right. So your answer is to the point. So for example, 1, 0, 0 is not in the span of S. Right. Okay. So now if I add 1, 0, 0, then will it become an orthogonal basis? So now third is adding 1, 0, 0, 0. So to S. So now is S does S forms a basis now?
Yes.
Right. So it is already because S is the only linear dependent. It's a linear dependent to other because it's not in the span. The second point is it is minimal spanning because of the dimension of MR2 is 4. So there are 4 vectors, so it is minimal spanning. Now, is it an orthogonal basis also? So it is a basis, that is correct. Now, is
It's
it an
not
orthogonal? It's not
It's not.
orthogonal?
It's
Why?
not. Yes, because if you check V2, V3, so M2,
V2,
sorry,
V3.
yeah, M2, M2. I mean, so M2, M3 is not the null matrix.
Why?
Um,
Let's do the inner product.
it's minus. The last entry would be minus 10.
So it is 1 times 0 plus 0 times 0, 0 times 4, 0 times minus 2, right? It is 0, right?
Yes, but if you take M2, M3,
What is M?
yeah, I
Oh,
mean V2,
M2,
V3.
M3, this one.
Yeah, 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 yeah.
This one, this one.
Still, I think
This
it is an orthogonal basis. That will also be 0.
Okay. So 5 by 2 times 4 plus 5 times minus 2. You cancel my 10 minus 10, 0, right?
Oh, I see. I see. I missed the point because you had defined this the inner space. So I missed that. Yeah, I missed the definition. Sorry. Yeah.
No, it's fine. Okay. So it is again going to be an orthogonal. So it's going to be orthogonal basis. So moreover, let me write that down. Moreover, uh, this new set with 1, 0, 0, 0 and remaining other 3 vectors is an orthogonal base. All right. So I hope this concept of orthogonal base is clear to you. So for orthogonal, given any minimal spanning sub orthogonal set forms a basis. Okay. Because orthogonality implies linear independence. So you don't need to check linear independence. So, right. Now let me come to the topic of orthonormality. Okay. So orthonormal simply means that you are considering vectors of unit length. Okay. So similarly, you have a concept of unit length in R2. So where you divide your vector with their length and you obtain a vector of unit length. Similarly, in abstract vector spaces as well, you can divide your vector by the norm of that vector and obtain a unit length or unit norm vector. And these unit norm vector are called normal, orthonormal. They are called normalized vectors. And if you have an orthogonal set and the orthogonal subset such that each vector is of unit norm, then it is called orthonormal. So let me write down the uh, orthonormal set. Or subset of vector. So let's say you have given a set of vectors v1 of vk in V, such that first point is that this S is an orthogonal subset. All right. And the second point is that the norm of each vi is 1. Okay. So what does this first condition implies? This first condition implies that vi vj is vi vj is equal to 0 for I not equal to j and I and j both varying between 1 to k. The second condition says VII is equal to 1, which is also equivalent, to say that norm of VI with itself, the n product of VI with itself is 1. All right. So this is what the orthonormal subset looks like. Again, we know that orthonormal, because orthonormal subsets are orthogonal subsets, so they are linear dependent also. Okay. So we know that orthonormality implies orthogonality, which implies linear independence. Okay. So this is the first independence is by the definition, and the second is the fact that I mentioned above. So an orthonormality implies an orthogonality, and orthogonality implies an independence. So any orthonormal, again, so any minimal spanning orthonormal set any minimal spanning orthonormal set forms a basis. All right. And again, we can define orthonormal basis. So a basis is called orthonormal if, let's say, the bases are given by b1 up to bn of your vector space of n dimension. That this is called orthonormal if b1 up to bn is an orthonormal set. And second, just it need to be this orthonormal set. That's it. Okay, so a minimal spanning orthonormal set gives you an orthonormal basis. All right. So now let's look at the example that we did earlier. So we had this example. Okay, now let me ask you this. So if I have orthogonal subset, which is V1 up to Vn in V, then how do we obtain orthonormal subset? So we need to divide each of the vector with its norm. All right, and we obtain an orthonormal subset. Okay, so let me take the example that we discussed earlier of the subset in option 2, which was so we saw that this subset of 3 vectors was orthogonal. Okay, now how do we obtain the orthonormal set from this subset?
So the norm, we divide make the first vector by its norm, the second and third by its norm.
Yes.
So the norm will be
Vector?
just 2 by 2.
What is the norm of the first vector?
2.
2. Norm of the second vector is root 5. What is the norm of the third vector?
Root 5 again.
Right. So we get 1, 0, 0, 0, 2 by root 5, minus 1, root 5, 0, 1 by root 5, 2 by root. All right. Okay. Now, why orthonormal bases are important? Okay. So orthonormal bases are important because why orthonormal? Why orthonormal bases? All right. They are important because if you want to express a vector, so any vector in V can be expressed with respect to the linear coefficient, some linear coefficients, with respect to some linear coefficients of AIs, okay, in some combination of AIs, VIs. Suppose you have a orthonormal basis given by V1 up to V of V, then you can express any vector in terms of a linear combination of these V's. Now, we don't know. We know that we can express that, but we don't know what those AIs are, right? So in order to find out those AIs, in case of the orthonormal basis, it is much simpler. All right. So how do we obtain these AIs? So you just need to multiply each of the basis vector. In order to find out AI, coefficient AI, you just find out its product, inner product with VI. Okay. And then you will see that if you express A1, V1 plus up to A and Bn, this vector, and you perform the inner product with Vi, now use the linearity. Okay, use the linearity of first coordinate of the inner product. So you will get AI Vi, AI V1 plus Vi up to there will be some AI term, and then there will be the last AN, Bn, Vi. All right. Now what happens to the first term? What happens to the first term?
It's 0, right?
It is 0. Why it is 0? Because V1
VI,
and Vi are
0.
orthogonal to each other. They are orthogonal to each other. So the first term is 0. second term will also be 0, and the last term will also be 0, except the ith term. So ith term will become what? So only the ith term will survive, and you can take ai out because it's an scalar. So it becomes ai. All right. So what we have noticed that uh, so we have noticed that ai is nothing but the inner product of p with bi. So it will be easier for all I from 1 to k. So that's where it is used. So that's where working with orthonormal basis is more convenient than working with any arbitrary basis. Okay, because you can express your coefficients in terms of the inner product. Yeah. Any question?
So I have a question regarding this. Like when you do this, linear expansion and
Right.
these vector v, and when you take the inner product of v with vi, so is it like
Ah.
in the more geometric sense? Does it translate to the fact that you are taking the projection of vi
Exactly.
across v?
Correct. You are absolutely correct. This is precisely the projection that I'm taking in the direction of VL. Yes, you are absolutely correct. Yeah. So this leads to me to the topic of projections. So I was about to discuss projections only, and thank you for motivating uh, towards that. So as you have correctly mentioned, that in geometric setting, it it is nothing but the taking projection of your vector v in the direction of vector vi. Okay, and this coefficient ai basically tells you that it is ai scalar in the direction of vi. Okay. Uh, to be more precise, what I'm trying to say is that let's consider this with the standard basis in R2. Okay, so in R2, we have a standard basis E1 and E2, right? In R2 with dot product. So first of all, we already know that E1, E2 forms they are orthonormal basis. All right. It is easy to check. If you take the norm of E1, it is 1, norm of E2 is 1, and they are orthogonal to each other. So they form orthonormal basis. All right. And now if you express any vector, let's say, let me draw the graph again. All right. So E1 is this, and this is your E2. All right. And any vector, let's say this is 2, 2 vector. Then if you project it down onto x-axis, then you get the scalar in terms of E1. And if project it on the y-axis, then you will get the scalar with respect to E2. Okay. In other words, the times of scale you need to do, or in particular, that you need to scale your vector even twice in order to obtain the length that it projects on the x-axis. Okay. So if you express your if you want to express 2, 2 with respect to the orthonormal basis, what you need to do, you need to take the inner product first with E1 to get A1. And what we will get? You will get 2. And A2 is again inner product with E2, which is again 2. So this length is twice E1, and the vector that you project on E2 is also again the twice of E2. Okay, so in other words, yeah, so this leads to the fact that I have projected my vector, this vector b in the direction of E1, which is 2 times E1, and projection of v in direction of E2 is 2 times E2. And how did I obtain 2? 2 was obtained by taking the scalar product, taking the dot product with respect to E1. Similarly, taking dot product with respect to E2. Is this projection clear to all of you? All right. Now this is, I projected these vector with respect to the standard basis, okay, or onto the standard basis. I need not to be, I can project any vector on any vector, okay. So instead of taking, let's say, you may take vectors to be, let's say this is 2, 1 vector, and let's say this is your 1, or let's say 0.7, 3. Okay. Now I want to project this vector. So call this vector to be W and the vector below to be B. I want to project this vector W onto vector B. Okay. So how do I project that? So to projection, you need to find out uh, the shortest distance between this point 0.73 and the vector B. Okay. And this is where, and wherever this dotted line intersect this, that's what the projection is, and how to find it computationally. In order to find this computationally, you need to consider the dot product of W with respect to B. Okay, that gives you the scalar. This is scalar, and the direction you will get. So projection of W in the direction of B is precisely given by B dot product of B with W, and now you need to multiply with the unit length direction. Okay, so what is the unit length direction of B? It is V divided by its norm. Okay, so V divided by its norm. That's the unit length. Yeah. Any question? So this is how one can project projection of a vector onto a vector.
See here, it's the projection of W on B.
Yes, this is the projection of W on B. So you may write it like W, right? But it is all same. So this is how we define projection of W on B. And how do we define projection of V on W? We will define it to be
B comma
the
W
dot.
and W by
Yeah.
W.
Yes. Only the direction will change. The scalar will remain same because so direction will change, and this. All right. So for example, in this example of 2, 1 and 0.3, 7, and this is in R2, and I'm working with dot products. So what is the projection of W with respect to in the direction of B? It is projection of W in direction of B. It is basically the dot product first. So with what is V dot D divided by the norm of B direction in the direction of B. So what is V dot B? V dot B is 2 times 0.7 plus 1 times 3, correct? Divided by uh, 2 square plus 1 square square root of 4. You will get 1.4. 1.4 plus 3, 4.4 by root 5. This is scalar. You need to multiply 2, 2, comma 1. You will obtain 8.8 by root 5, 4.45. Okay. Is this fine with everyone?
Yes.
Good. Now, as I have projected a vector onto a vector, okay, this can be think of it as projecting a vector W onto, so let me copy this. As I have projected a vector onto a vector, this can also be think of as projecting your vector W onto the subspace form subspace spanned by vector B. Okay, so this is the red line is precisely the span of V. Okay, now what is the span of V? It is AV, where A is a real, right? It is clearly a span in R2. Okay, it forms a line. So projecting W onto V is also similar to projecting your vector onto a subspace in your vector. All right. So now, if I work in higher dimensions, okay, let's say in Rn, so there can be subspaces. There can be subspaces. For example, if I am in R3, so there can be a plane like this, and there can be a vector going W like this. This is actually the origin, and these are my axes. X, Y, Z. All right. So this is my W, and now I want to project W, my vector W, onto this subspace W. Okay. Now how do I do that? So these projections also make sense. Okay. And for that, in order to uh, find out these projections of a vector onto a subspace, first we need a basis, an orthogonal set of basis of W, orthogonal basis of W. All right. So, and once you have orthogonal set of vectors on W, then you can take projections on each of the vector in that basis, and you can sum those projections. All right. So let me, yeah. So let me give you. So let me, before introducing projection on subspaces, let me talk about projections onto the span of a orthogonal set. So projections projection of a vector onto a span of an orthogonal subset. Okay. So let's say my subset of orthogonal vectors are V1 to Vk. All right. So I define the projection. So the projection of, so first let S denote the span of V1 to Vk. Then we define the projection of W onto the span of these vectors to be the projection of W with V1, projection of W with V2 up to projection of W with VK. All right.
Yes.
So this is how we obtain the projections. So in shorthand notation, you can just simply write it to be projection of Vi, projection of W with respect to Vi, where I is varying from 1 to K. All right. Now, the question is, if you want to project a vector onto a subspace, what you need to do? You need to first find out an orthogonal basis of that subspace. So once you have the orthogonal basis, then you can project your vector onto with respect to that orthogonal basis, and the formulation will look like this. All right. So let me uh, discuss an example. Right. So we have noticed that this subset of vectors in R3 with dot product. So we know that S is an orthogonal subset, right? Is S an orthogonal subset? We have already seen that,
Yes. Yes, it is.
right? So it is an orthogonal subset. Now I would like to project vectors V. Okay, so first vector V is 1, 2, 3. So what is the projection of? So let me also define W to be the span of S. Okay. So now what is the projection of V with respect to W? Let me also use notation V1, V2. Now, the second vector is half 0, 0. Third vector is 0. Right. So what is the projection of B? What is the projection of B? First one.
So it's B dot V1 times
So it is,
V1 by times of
no,
V2.
this is the formula, right? Now, what is projection of B with respect to V1? First, we need to do the dot product.
Yeah.
It is V dot V1. What is that? V dot V1 divided by
It's
norm
2.
of V1 in the V1 direction. So it is V dot V1. V dot V1 is 2. Norm of V1 is what? What is the norm of V1?
2.
2. And V1 we know. So it is just V1 plus what is V2? What is V1 dot V2?
It's 1.
It is 4 minus 3. Right. 1 divided by norm of V2. What is norm of V2? Norm of V2. What is norm of V2? Norm of V2 is
Root 5. Root 5.
4 plus 1 square root. So it is root 5. Right. And then we have V2. So it is root 5 V2. Right. So if I,
For
right.
V. Okay. Yeah. No issues.
Now, what is the vector? What is V1? V1 is 2, 0, 0 plus this. So, what this vector is going to be 2, 2 by root 5 minus 1 by root. Correct? Now, what about V in the second? Again, what is the projection of V onto W? So first we need to find out the projection of V onto V1 plus projection of V onto V2, right? Now, do you guys notice anything about V2, about
V
V1?
V is 1 by 4 times of V1.
So it's a scalar multiple of V1, right?
Yeah. Yes.
So its dot product with V2 has to be 0 because they are orthogonal to each other, correct? So the second term will go away, it is 0. Only the first term will survive. Now, what is the first term? If I do the dot product of V1 with respect with V2, sorry, V1 with V. So what will get V1 dot, I will get V dot V1 divided by norm of V1. Now, what is V dot V1? It is 1. 1 by 2, 2, 0, 0, which is going to be 1, 0, 0. Right? Now, similarly, for projection of V in W in the third case, it will be equal to the projection of in terms of V2 only, because it's a multiple of V2, right? It is a multiple of twice multiple of V2. And if you perform the dot product, you will get 8. So I leave this for you. So you let me know the answer of this. Okay, so what we have noticed in these examples, that projection, what does projection do? So projection, so these projection, it acts on a vector and it gives you another vector, but that vector lies in W. Okay, so projection of W, projection onto W, what it does, it takes a vector in your from your vector space and it gives you a vector in W. So in other words, it defines a map. So it takes V and it gives you projection of V onto W, which is a vector in W, right? That's what it has done, right? These vectors, for example, 1, 2, 3, it has projected back into a vector that is in the span of S, correct? So, so it defines a map from vector space V to a subspace, to the subspace W. Now, what is the now what are the properties of this map? The first question is, first point is it a surjective map? Is it a surjective function?
Yes, it
So
should
W
be.
is a subspace of, right? W is a subspace of. So if you take any element from W, it will project to that element in W, right?
Right.
So yeah, so it is a surjective map, correct? So yes, it is a surjective map. Now, second point, is it linear map? Is it a linear map? So for linearity, we need to check what? We need to check that V1 plus alpha V2. Okay. If I apply projective, if I project this element onto W, then it should be equal to projection onto of V1 plus A times projection of V2, right? This is what the condition that I need to check. So I start with the LHS. Now, what is the LHS? LHS is the projection of V1 onto V2. So you need to have basis, orthogonal basis of W. So so suppose E1 up to EK denote the orthogonal basis of W. Okay. So here I'm using a fact that any vector space can have a orthogonal basis. I will discuss that fact. I will discuss that fact in the next session. Okay. But for now, you can assume that that is true. So suppose E1 to EK denote the basis of orthogonal basis of W. Then you can use these bases to express this projection. So projection of W is nothing but what it is. It is going to be summation of projection of V plus alpha V2 with respect to each of the basis vector, right? Now, if I look at just one of the, so it is sufficient just look at one of the basis vector because, right, projection onto one of the basis vector. Now, if you look at the definition, it is the linearity that I'm going to use. Norm of this times EI. Now we know it is linear in nature, so you can rewrite it as like this. All right. Now this again becomes the projection of V1 in the direction of EI, and this becomes the projection A times the projection or alpha times the projection of, which is alpha I star alpha times the projection of V2 in the direction of E1, right? EI. And yeah, and you do this for each of K. So thus we obtain RHS. So we now you just do this for each of I varying from 1 to K, and you replace uh, this linearity with respect to each vector. Okay, in this expression. Okay, and then you will get one thing on the right hand side. So it is a linear map, right? It makes sense, right? So I've used a fact here. So I will discuss this fact in the next session, that how to obtain orthogonal basis for any given vector space. Okay. Okay. So this defines a linear map from V to W, right? And it is a linear transformation as well. Okay. So any doubt till this point? Right. Okay. So now let's move on to discuss an example because we have seen enough theory. So an example would be nice. So let me start with the example that I gave earlier. P2x. Okay. Do you remember this space? This was the vector space of all polynomials of degree smaller than or equal to 2. Okay. So let me rewrite it convenience. All right. And how did I define? I defined two type of inner product on this. I will be using the integration. Okay. So I defined this product to be P x times qx dx. Okay. So it is inner product on Px, Qx, where Px is A naught, A1x, A2x square, and Qx is B naught, B1x, B2x square. All right. Now we have already checked it is an so yeah, it is an exercise for you to check that it is an inner product space that I've already given. So I will not I will not give that again. I will not write that again. So now let's check this part. So check that set S given by 1 x square is an orthonormal subset or not. Okay. So how do we check that it's an orthonormal subset or not? So this is your V1, this is your V2, or better P1, P2, P3. So now P1, P2, you need to check orthogonality, mutual orthogonality, right? So is P1, what is the inner product of P1, P2?
Yeah, it's orthogonal because P1, P2 would be 0, P2, P3 is 0, and P1, P3 is also 0.
Is it?
Oh, okay, you are
Is
defining
P1,
this
P2,
by with integration. Okay, okay, yes.
right? So is it 0?
No, it's
P1
x
is 1
dx.
times
It's
x.
half.
Yeah, so it is going to be, it is non-zero. Similarly, P2, P3, this integration is going to be x times x square. It is non-zero. And P3, P1 is also non-zero. All right. Right. Now, they are given to be an orthonormal set. They are not orthogonal set, as well as they are not the orthogonal set. But are they linear independent? Does the set S, so does S linear independent? So is S linear independent? How do we check that? How do we check linear independence? What is the definition of linear independence?
Should be a minimal spanning set.
It's A1, B1, like A to B to the coefficient should be simultaneously 0 to get that.
Yes. So let me write that A1, A1 1, A2 times X, A3 times X square, right? If this is equal to 0, if and only if A1, A2, A3 all has to be equal to 0, then only they are independent, right? So I start with this equation that A1, A2, A1 plus a2 plus a3 is equal to 0. Now it is a polynomial that is equal to 0. Now when does a polynomial equal to 0? If all of its
Coefficients is 0.
right? So this implies that a1 equal to 0 equal to a2 equal to a. All right. So it is a linear independent set. So S is a linearly independent set. All right. So it was pretty direct. Now the question is, how do I get a orthonormal set, orthogonal set out of this linear independent set? Okay. So how to obtain the orthonormal set, or in particular orthonormal basis in this case, because it is minimal spanning as well. So how do we obtain orthonormal basis from this non-orthogonal set of vectors? Okay. So that's where these projections becomes handy, and that's where we talk about this procedure of Gram-Schmidt method. Okay, so Gram-Schmidt procedure Gram-Schmidt procedure is a way to obtain an orthonormal basis for orthonormal set from a given set of vectors, or a given linear independent set of vectors. So let me write down the general description of it, and then we will work out this example. Suppose v1 up to v1 up to vm is a linearly independent set of vectors in V with inner product. All right. So now so because we want, what do we want? We want an orthonormal. Okay, you need to be careful that I'm talking about orthonormal, not orthogonal only. Orthonormal basis, or in particular orthonormal subset out of this vector from V1 up to Vm. All right. So for orthonormal, what is the conditions? What are the conditions? Orthonormal subset, that it has to be an orthogonal subset, first of all. And the second condition is that the norm of each vector should be equal to 1. So I define my E1. So it is an inductive process. Okay. So I define my E1 to be V1 divided by its norm. So for E1, I take the same vector and divide it by its norm, V1 by norm of V. All right. Now E2. So E1, E2, EK will become the orthonormal basis. Okay. So now I define E2. So E2 is defined as V2 minus projection of V1, projection of V2 in the direction of V1. All right. And then you divide by the norm of this vector. All right. So what are we saying? We are subtracting the part of V2 that projects onto V1. Okay. By doing this subtraction, we make E1 and E2 orthogonal to each other. Okay. So once you subtract this projection part, whatever is remaining, that becomes orthogonal to each other. Okay. So yeah. So let me show you that why they are E1, E2 are orthogonal to each other. So E1, E2 they are orthogonal. So let's not worry about their inner product. Let's not worry about their norm for the moment. So what is E1? E1 is this. What is E2? E2 is V2 minus projection of V1 divided by the norm. I'm not writing that, it's a big number. All right. Now, by linearity, I can take this thing out. Okay. So I will take this out. And again, by linearity, I can take this out. What is remaining is this thing. Yeah, sorry, there is a vector as well because projection. Oh, sorry, this is fine. Yeah, this is fine. Right. V1 position of this divided by the norm. All right. Now by symmetric properties, so let me this U AV. So recall that this is equal to by symmetric behavior of the inner product. This is equal to AV U. Now you can take A out because by this fourth property of the inner product. So this becomes this. So this is again. So in the second coordinate also, the inner product is linear. You can check that using the symmetry. Okay. So I can take the other inner product out as well. All right. So let's do that. So I've taken these two inner product out. Now only thing that is remaining is these two things. The inner product of V1 with the inner product of with V2 minus the projection of V2 in the direction. Okay. So if you look at this, what is this expression? This is now we can use again the linearity in the second coordinate. So using the linearity in the second coordinate, we obtain this minus V1 projection of V1 V2. All right. So I'm focusing on this term. Now what is the projection of V1 of V2 in direction of V2? It is V2 V1 divided by norm of V1 times V1. Right. Now just place that thing over here. Now this whole thing is a real number, so you can take this out. So get all right. Now this is a real number. You can take it out. So what this remaining is V1 V2 minus V2 V1 divided by norm of V1. Inside it is remaining V1 V1. All right.
Sir, in this step, step where you use the linearity property with V1, V2
Right.
minus projection of V2, so there we got this V2, V1 inner product times V1 by norm of V1, right? So now, since this V2 V1 by norm of V1, this term and the first term, which is V1 V2 by norm of V1 again. So these
Right.
two are similar terms, right? We can pull them out, right?
Yes. Right.
Yeah.
That is true. I there is I think there is a problem.
So when you do this and get this term,
Right.
like
So
V1 V2
uh,
by this norm of V1 out, so you get,
mm,
so if we spool up this one by that norm of the other thing, which is still a real number, so we get only this V1 comma V1 and V2 inner product, right? That's only left out.
yes. No. So what is there is that right. So yeah, till this point it is fine. Uh, Now we notice that earlier we have removed this 1 over norm of v term from the expression. You can take this term inside, and instead of taking it in the first coordinate, you can take it in the second coordinate. Uh, okay. Uh, so I will update this on notes. So, but there is some computational error I can notice here, because if I take this is norm of v1 square, and this is norm of v1, right? This is what I will get, but I was supposed to get rid of this v1, norm of
Yes, it
v1,
should have been zero
and
actually.
huh?
I mean,
Sorry,
yeah, I mean, this
can
thing
you
should
please
have
repeat?
been zero. Yeah, so
Yeah,
this
this
thing
thing
have
has
been
been zero. Yeah,
zero, yes.
yeah. So there is some computational error which I'm not able to figure out as of now, and I don't want you to bother about this thing because uh, these things are these things are part of proof, and it is kind of you can find it in any standard text. I will update these on notes. Okay. So what the point is like that after doing this procedure, the vector that you will obtain. So that's why we are removing this factor. So this factor removing this factor becomes important because after removing this factor, it becomes orthogonal to the first vector that we started with. And we keep on repeating this until so we keep on repeating this. So for example, in E3 obtaining E3, we remove from V3 the projection with respect to V1 of V3, projection with respect, sorry, here it should be E1. Oh, okay. That is what I did. Okay. So this is a projection with respect to E1. Yes. Now I notice the mistake. Yes. So I am removing the projection of V2 in the direction of projection of E1, not V1. Now V1 is gone in with respect to E1, right? Now it is fine. Projection with respect to E1, projection with respect to E1, right? Projection with respect to E1 is this. Right. Now, when I write projection with respect to E1, now what is E1? Precisely, E1 is precisely, yeah. So I will get projection E1 below and here as well, V1 by E1. And here it will be uh, move down, it should be minus equation. No, this one. This is already one. So remove this, and now we are okay. Again, the problem remains the same. Oh, right. It is. I just need to write even only. It's even all over, and it is. Right. Right. So now it is written. Okay. Yeah, I did that mistake. Okay, so what I will do, I will start this thing, Gram-Schmidt process, in the next session. Uh, I don't think it is a good time to keep on this. So today's takeaway is that we learned about orthogonality. We learned about the orthogonal subset, how to form an orthonormal subset from a given orthogonal subsets. Orthogonality implies independence. So any minimal spanning orthogonal set forms a basis, which is orthogonal basis, and similarly you can obtain orthonormal basis as well. Then we saw these projections onto vectors onto a subspace. All right, and then we saw this example where we have this inner product onto the polynomial of degree less than equal to 2, but this set is linear independent, but it's not orthogonal set or orthonormal subset. How do we form the orthonormality? We need Gram-Schmidt process, which can convert any independent set into an orthonormal set, which we will discuss in the next session. So today's session stops here. This Gram-Schmidt process will be due for the next session. Any question you may ask me. Thank you for joining. Yeah, I will start with Gram-Schmidt process in the next session on this one. Yeah, thanks for joining.
Thank you, sir.
Okay. Yeah, thanks.